I would like to thank the organizers. This is a really nice conference, and also for the really nice weekend that some of us already had, and also for giving me the opportunity to present what we have done so far at ICFO. So today, as I try to sketch in this artistic view, I will explain how by mixing two different Bose-Einstein condensates, we can create this exotic state of matter called quantum liquid droplet. I will explain some of the properties of these droplets and some of the current work that we are doing in our lab. Okay, so just to start with, let's put a general frame and let's first speak about fluids. So fluids, we can find them in two different phases, either in the gas or a liquid phase. It will just depend on the interaction strength between the particles or the distance between them. In fact, if I put these particles in a box, I can reveal the different properties of these two systems. In the case of a gas, as we know, it will just occupy the volume of the container. Actually, in fact, I can reduce to half of the size of my box, and I will also reduce the size of my gas. So we know that gases, they have really high compressibility. In the case of liquids, as we know, they have some fixed volume that will just take the volume of it has a fixed volume. And then if I want to reduce the size of my box, it will be a really challenging task. So liquids in general has low compressibility. Some other difference between these two systems is that liquids, they have surface tension, and therefore they can form droplets. And droplets are in general cell-bound states that appear due to the balance of attractive interactions that basically hold the system together, but repulsive ones that avoid the collapse of the system. So usually in normal liquids, these interactions, they come from these two-body potential, and as we know at large distances, so they attract by van der Waals attractions, but however at short distances, we have this hardcore repulsion. So in general, liquids, therefore, okay, so in general, liquids, therefore, are dense systems because we need some characteristical length scale where these two terms, they can balance. And that's why liquids are complex systems to model. And on top of that, one of the properties of these liquids is fully defined by the details of the potential. Therefore, I need to know all the details of the potential in order to obtain the properties, in order to describe my liquid in a better way. So the question that I wanted to address at ICFO is like, I'm sorry that this is not working. Okay, the question that we wanted to address at ICFO is like, okay, can we make a dilute quantum liquid where we can overcome all these problems I just mentioned before? And of course, I don't have to explain to you that quantum gases are really good systems to overcome these dense systems, and also to define it with just single parameters, so-called, for example, the scattering length. So with this, I come to the outline of my talk. So first, I will explain like how to go from quantum gases to these quantum liquids. I will explain the experiment that we have performed at ICFO. So we can observe these quantum droplets in the mixture of Bose-Einstein condensates. And finally, if I have time, I will also explain the difference between solitons and droplets, because in fact, these two systems are cell-bound states, or at least bright solitons are well-known cell-bound states that exist in the community. Okay. So as I explained before, so okay, how can we create a liquid using a gas or using a Bose-Einstein condensate? So first we need attractive interactions to hold the system together. And in fact, in BECs, this is pretty simple because we can just use flashback resonances. So therefore, I can tune the interactions in my condensate to attractive. But this will be the mean field energy associated to my Bose-Einstein condensate that depends on the scattering length and the density square. But however, at this length scale, there is no repulsion that can stabilize the system. And what will happen is that just my BEC will collapse. And in fact, this is something that was studied during the early times of BECs, where this BEC of the collapse was revisited in these different papers. But this is the end of the story. So Dima Petrov in 2015, he realized that, okay, maybe instead of using just one single component Bose-Einstein condensate, we can use two component Bose-Einstein condensate, which has repulsive interactions, each condensate, but attractive interactions between them. In this system, I can define this concept of this delta A that will depend on the difference between the inter and interspecies interaction. I can also define my mean field energy as I did for the single component Bose-Einstein condensate. This will depend on delta A and n squared. But what is really interesting is that in this two-component condensate, we have some extra repulsion that becomes important that comes from quantum fluctuations or beyond mean field terms. This repulsion depends on the scattering length A, and it has a scaling on n phi half on density. This means that I can find a situation where I can tune my delta A close to 0, or maybe even 0, and kill, therefore, this mean field energy, or make it really small, and comparable to the quantum fluctuations, or this repulsion extra term that can stabilize my system. So therefore, for a given delta A negative, I can find an equilibrium density that will depend on just only interactions, and therefore this will be more or less the phase diagram. For delta A positive, I will have a Bose-Einstein condensate, but for delta A negative, I could find an equilibrium density that will stabilize my system. This is a very exotic liquid because, first will be self-bound using just two-component Bose-Einstein condensates. It will have some surface tension. It will have some very weak compressibility. And what is an interesting property is that it will have some homogeneous bulk density. Because as I explained before, the equilibrium density just depends on the interactions. So once you have the right interactions, if you put more and more atoms, the density has to be constant. So therefore, this is the wave function or the profile that I expect to see. So for a given equilibrium density, I will have a flat top density profile, and this will be part of the surface of our droplet. If I put more atoms, just this wave function will increase. For the experimental parameters that we use in our lab, so this is a really ultra dilute liquid that in fact is like 8 orders of magnitude more dilute than any other liquid in nature. And the advantage is that it has a very simple theoretical description because it's made only of isotropic contact interactions, or the scattering length A. And the advantage, or something that is really nice from these droplets, if they exist, is that the appearance is just due to the strong effect of quantum fluctuations. And this is what I will show. If you want to have more details about the properties of these liquids, so there is a really nice review from Dima Petrov, where he explains how these liquids go beyond the van der Waals paradigm. Of course, this is not the only system that droplets could exist. They can also exist in dipolar droplets, and this is something that already in the group of Tillman, Fao, and also Francesca Ferlaino have shown. The analogous example from between our composite droplets on these dipolar droplets is the following. In the case of dipolar droplets, as we know, they have the contact interaction that they can tune via magnetic field, but they also have the dipolar interaction that they can control depending on the geometry. In our case, that is the composite droplets, we have the interspecies interaction that depends on A, and the interspecies interaction and the interspecies interaction. In that sense, both systems, they have two different interactions that they can help to control the mean field and kill this mean field energy, and then observe this Lagrangian correction. So with this, I go with the second part of the talk. So the idea of this Bose-Bose mixture is that first, we need a Bose-Bose mixture that allows us to have this parameter delta A, A up, down, lower than 0. So of course, in our experiment at ICFO, we work with potassium, so we can find, or we could have very different possibilities. We can either work with dual Bose-Einstein condensates of potassium 39 and 41, or different spin mixture of 41 and 39. So what we have done before is to do an extensive study of all the different resonances that we can find in the system in order to find the regime where we can find this window to create these quantum liquid droplets. Experimentally, we found that the best is using two spin states of potassium 39. In particular, I will call from now up and down to the F equal 1, MF equal 1, and F equal 1, MF equal 0. And this is what I call the magic magnetic window, because at this magnetic field, we have the overlap of 3 different Feshbach resonances that allow us to perform this experiment. So we have 2 that are repulsive for the states up and down, and then we have the interspecies interaction that is attractive. Therefore, I can define my parameter delta A as I show here. Here will be delta A positive, and for here there will be delta A negative. And this is the magnetic window we will use in all the experiments I will show. So the experiment, we performed the experiment in the following geometry. So we load the Bose-Einstein condensate in one single plane of this lattice potential. Even though that I use the word lattice, so we work in the bulk, so we don't have hopping or hover Hamiltonians. So all the dynamics that I will present, they are constrained to this plane, and this blue detuned lattice potential just give us some small vertical confinement in this direction, and this is just to hold the atoms against gravity, and some weak radial anti-confinement. What we perform and what we will show in the picture is in situ images that we use a phase contrast imaging technique. And as I explained, I mean, we don't use time of flight. It's all in situ, and all the dynamics will be constrained to this plane. So let's start with the first experiment. So what we did is first we use a single component Bose-Einstein condensate. So we prepare our system around here at 68 knot. It's just single component. We remove the box that I just explained before. And then this is the kind of images we see, the dynamics on time. So as we expected, it's a Bose-Einstein condensate that behaves as a gas, and it will just expand a long time. So now, what happens if I now tune my scattering length to negative? As I explained before, in the case of the single component Bose-Einstein condensate, should just collapse. And in fact, this is what we observe. Now we go for the second experiment. So we go to the magnetic window that we like. We have our delta A parameter, as I explained. So we start with a Bose-Einstein condensate in a spin up. Then with a radio frequency pulse, we can do a spin mixture of the two spin states. And then we tune the scattering length, delta A parameter. The first experiment, so we do delta A positive, and as expected, we observe that it just expands as a gas. But then here is where the magic appears, and we were really happy in the lab. It's because in the delta A negative regime, at least in mean field theories, we should expect that our mixture should just collapse, as I presented in the slide before. What we observe is the formation of a cell-bound state that can propagate for tens of milliseconds. And this is what we call the liquid. And then just I do a zoom, because of course we were really happy when we saw this result. And it's important to remark that similar experiments, they have been done nowadays in lens, in the group of, in this paper, Giulia Semigini. And all the results I will explain now are complementary to the results that also in lens has been working. Okay, so now let's analyze a bit the data that we observed in the lab. So the red points I will show, it's the gas, so the delta A positive system, and the blue points is delta A negative, so it's the droplet phase or the liquid phase. First, if we observe in data number, or the size as well, the size we can see in time that it just expands as a normal gas, but we see that in the case of a liquid, it just remained cell-bound. What we observe also as well is that the atom number decay in the case of the droplet phase, while in the gas phase, it just remains constant. And this we attribute this decay in atom number to three-body combination. And this is because our droplet remains cell-bound for a long time, so the density is pretty constant. So that's why we observe these losses up to a point where this three-body recombination is not more important. In the case of the gas, because it just expands really fast, so it becomes really dilute, and then that's why we don't observe this effect. What is interesting is that if we zoom this part from here, we will see that, yes, the liquid phase, it's constant, the size is constant just for tens of milliseconds, but then it grows up. And this is because before what I present is I was just taking into account the mean field energy and the Lagrangian. But also we know that we have quantum pressure that in this case, for low atom number, the scaling that depends on n becomes important, and actually this is what dissociates our droplets. So what we are observing here is that for low atom number, the kinetic energy is actually driving a liquid to gas phase transition in the system. We have plotted this in the size and as a function of atom number. So what we observe is like for a given atom number, the size remains constant, but then for a critical atom number, this size diverges. And this is where the transition occurs in the system. We have as well observed the same if we plot in terms of density, where the density remains constant and then just behaves exactly like a gas, as I show here in the red points. So using these observables, we can extract the critical atom number, or we can extract where this transition occurs as a function of the atom number and also as a function of the interaction strength. This is what we have done. And then as I show here, depending on this delta A, as we can observe, when this delta A becomes stronger, so we need less and less atoms to remain this system self-bound. That is more or less what we observe also here in this phase diagram. And then we have made this kind of plots for different interaction strength, and this is what I show here. This will be the line for the phase transition. Above is the liquid, below is the gas. We have also plot for a given atom number, the sizes that we can resolve in our imaging system. And we have compared this with the theory and adding this Lagrangian correction. And what is interesting is that, okay, using no fitting parameters, this theory fits, I would say, quite well with the points. And then what is interesting to remark is that the system is a very sensitive test of beyond field theories, because the existence of this quantum liquid droplet is due to this Lagrangian term. And just to give you a flavor why these liquids are nice, okay, this is the two-body potential I presented before. So we have the attractive part and the repulsive core. And in the case of a liquid, basically liquids, they look like this. I mean, we have the core, that is this red part, and then we have the blue, that is the attractive one, and they are really dense and they are really close together. In the case of dilute, what happens is that this potentially doesn't even play a role, and the atoms, they are really, really far apart from each other, but still they want and remain together. So this is the picture that you should take from these ultra-dilute liquids, but really the atoms are so far apart, but still they remain together and they have some surface tension and properties of liquids. And again, I mean, I have this nice review of liquids beyond the van der Waals paradigm. And time, yes. Okay. So now I will explain, okay, what I have shown up to now is just these quantum droplets that are self-bound states, but however, bright solitons are also self-bound states that we know in the community, so I will explain now the difference between the quantum droplets and the bright solitons. So droplets, as I explained before, they appear due to the balance between the mean field and the quantum fluctuation term. However, one component bright solitons, they appear due to the balance of the quantum pressure and the mean field energy. In our system, if we place a Bose-Bose mixture in an optical waveguide, what it will happen is that we will have these three terms, the kinetic, the mean field, and the quantum fluctuation part, and both, at some point, the effect of the three will interplay. So what I will expect to see is either a transition or a crossover between the two systems, because the three energy terms, they play an important role. So what we have done is the following experiment. So we have played our Bose-Bose mixture in the same magnetic window and using the same imaging technique that I explained before in an optical waveguide. Here, I refer to quasi-one-dimensional physics in the sense that we constrain just the transversal degrees of freedom, but the longitudinal degree of freedom, is free to expand. And this is what we have observed. For delta A positive, so my system just expands as a normal Bose-Einstein condensate. But however, for delta A negative, we observe a self-bound state. So now, is this a soliton or is a quantum droplet? So we have performed the theory. We have used the Gross-Pitavsky equation, and with this additional Lagrangian term, and this is what we have observed. We have to do it numerically and also using a variational ansatz. So what you observe here is the magnetic field or interaction strength as a function of atom number. The color plot is the density. And what we observe is that we have low density solutions that, in fact, using the variational ansatz, we observe that the size of these solutions are in the order of the harmonic oscillator length. So therefore, these we call that are solitons. We observe that, well, that we have high density solutions. And in our variational ansatz, we observe that the size of these high density solutions is below the harmonic oscillator length. So this is what we identify as droplets. And what is interesting is that, in fact, we observe a bistability where we have the two minimas and metastable states and also a critical point, as I show here. So this is interesting because this bistability region It's similar like to have a first order phase transition. We observe that we have a critical point. We observe that we have also metastable states, and how these two minimas, they can appear or disappear in this bistability. So we have explored this experimentally, because what I have before is just a theory. So we have measured the density of this cell-bound state as a function of atom number and interaction strength. As you can see here, I mean, we have quite well agreement with the densities that we have expected to observe in the theory. What is interesting is this dashed line that I show here. This is the mean field collapse threshold, where I expect that my soliton should just collapse. And we see that we can form cell-bound state that goes beyond this field collapse threshold, which means that we have this extra term that actually is the Lagrangian term that is playing a role, and that's why our system is not collapsing. We have as well studied this bistability experimentally. So we have prepared solitons here, and then we have ramped down our magnetic field to cross the bistability and see what occurs. And what we observe is the following. We observe fragmentation of the system. And the way we explain this fragmentation is because this is obtained using our variational ansatz. So this blue and red line are the size of our soliton, I mean on this regime. And then when we cross the bistability, what happens is that we have a discontinuity on the density. Therefore, we go from this side to this side. My system cannot adapt to this discontinuity in density. That's why it fragments. We have measured the point where this happens, and this is the plot I show here. We measure the atom number in this small crop that I show here in these pictures, and we just see how this atom number evolves as a function of the interaction strength. And then we take as a middle point, we see that depending on the initial atom number, so depending where I start here, this fragmentation occurs in different points. So these are the experimental points that we have measured. And in fact, these lines are the ones I have explained just before. These are the bistable region. This black line from here is the transition where the two minimas, the soliton and the droplet, has the same energy. The top line is a metastable soliton. The bottom line will be a metastable droplet. And what we observe is that the fragmentation occurs on the top line, and this is because in the experiment that we are doing, we start with a soliton that enters in this direction, so it follows the minimum. Then at some point, this minimum becomes metastable, but still the minimum exists, so we just stay in the metastable minimum. But then at some point after this line, this minimum just disappears. And this is where we observe the fragmentation of the system. And again, it's what I was explaining before. And with this, I conclude. So this is what we have done so far at ICFO. Then now we have upgraded our system, and now we are studying coherent coupling of these Bose-Bose mixtures. So what we are able to do is via ref, we are able to coherently couple the two components of the droplets. And first, the first experiment we have performed is that when we go to this dress state, the scattering between the particles is not just the normal scattering between each condensate, but it's the scattering on the dress state picture of each dress state. And in fact, the effective scattering length of the system is given by the intra and interspecies interaction, and this value theta that depends on the detuning of coupling between the two states and the coupling strength. This is the way that, in principle, we can tune the scattering length. It can go from, I don't know, like, for example, 120 to 40. That will be 120, for example, will be I up, up, and 40 or 30 will be A down, down. So we can see that we can control the scattering length in this way. What we have done then is we have started with a pretty simple experiment. So we have our optical waveguide. We have a Bose-Einstein condensate. We do couple Bose-Einstein condensate in this waveguide, and then we let the system to expand. And with what we have observed, what I plot here is the width of the condensate as a function of, for a given time t. And as we know, depending on the interaction strength of the condensate, they will expand more or less. And in fact, this is the way that we can extract the scattering length of the system. And what I show here are the blue points where we can observe that, in fact, we are able to prepare this dress state, and we are able to control as well the scattering length. And this is just some Mill field theory that I put on top. Some last experiment that we did as well is because we can tune the scattering length. So now we go to a regime where, in fact, this effective scattering length can be 0 or negative. And then we have seen as well the formation of these dress solitons already, this optical waveguide. So now the question, or in the outlook that I want to give is that we will start studying also new kind of droplets that are coherently coupled. So other route that we are studying at DICFO is to go to low dimensions, either prepare droplets in 2D or in 1D dimensions. And with this, I think I can conclude, and I would like to thank my team, and in particular Leticia Teruel, that unfortunately she's not here, but she really wanted to come. But okay, and that's it.
Thank you very much, Cesar. Questions? Time for a couple of questions.